How many shaded squares are in this 10 by 10 grid? Do not count them one by one. Pause the video here and reflect on how you grouped the shaded squares. This is an adaptation of a Marilyn Burns task that we use to help students connect pictorial representations to expressions, first arithmetic and then algebraic. To begin, simply record students' thinking as arithmetic expressions. For example, this student sees 4 groups of 9.
4 nines.
Oh. So you're telling me that you're seeing 4 nines. Can you walk up to the board and just kind of show us the 4 nines that you're seeing? Because you're onto something.
9, 9, 9, 9.
Next, watch how the teacher presses students to make connections between the various expressions for counting the 36 squares.
Go ahead.
It's like the first one, but instead it's 10 times 4 minus the 4 corners.
Okay, good. So the -4, the darker maroon color, is subtracting the 4 corners. But if you remember the first slide, what's the difference in this representation? Jaylee.
Well, in this representation, instead of subtracting the 4 corners, it's not counting it as 10, it's instead counting it as 8 and then adding the 4 corners.
Very good. So we had 8 groups of 4 and then we added the 4 corners this time.
After students have had plenty of time to discuss how to represent different ways of counting the 36 squares with arithmetic expressions, it's time to algebraify them. We'll let the variable h represent the height of the square grid, and push students to transform their arithmetic expressions into algebraic expressions.
Yeah.
H is 10, which there's 2 10s, which is 8 plus h, and 10 minus 2 is h minus 2, which is 8, and which is 8 minus 2 plus h minus 2.
Okay, so the h minus 2 corresponds to which color?
Blue.
The blue. Okay, and what about the h?
The h responds to the red.
Very good.
So h is the red.
Watch how these students use the diagrams to make arguments and critique each other's reasoning.
So then down here you do h take away 3.
No, I think it's h take away 1 because 10 is supposed to be the height, but on this equation it's 9, so you have to take away 1 from the 10 and make
You can't because there
h.
is no 10.
Well, you can add the 10.
Because look,
Okay, so you can
hold on,
do-
look at this one, look at these two.
This debate continues for 2 minutes. Eventually, one student revises her thinking, not because the teacher intervened, but because the students were allowed to own the reasoning themselves. But don't take my word, listen for yourself. Do you think this student now understands why it is h minus 1?
Then how does this one write?
Because you would automatically think that the height of each square is 10, but it's 9 in this equation, so you would minus 1 first, and that would equal 9
now I
times 4, because it would equal to this problem right here.
So do you guys...
How does this expression relate?
To wrap this task up, the teacher asks students to relate the algebraic expressions they came up with to the pictorial representations. Notice how he asks a question to the class. Then he skillfully reads the room and decides instead to do a partnered turn and talk to make sure that all students are held accountable to reasoning about the question.
Basically 4 times 8, so that would be 40. And then it says subtract 4, so subtracting 4 would mean 36. So there is no answer with the outside of the box.
So you're telling me 4 times 8, but h is 10, which equals 40, minus 4 equals 36.
To extend this task, ask students, what about different size square grids? Would the expression 4h minus 4 work for any height? Notice how the teacher uses the dot cam to make students' thinking visible to the class.
It works because you can, when you do 4h, it equals the sides times 4, but since you're repeating corners, then the minus 4, that will get rid of the corners that are repeated, and that will get you an answer for 5 by 5, which would get you 16, a 12 by 12, 44, and the 7 by 7 is 24.